Hi everyone, this is lecture video 7, and in this video we talk about limits involving infinity and asymptotes of the graphs. So we investigate the behavior of a function when the magnitude of the independent variable x becomes increasingly large, like x goes to plus infinity or minus infinity. We further extend the concept of the limit to infinite limits, and we use this limit ideas to analyze the graphs of functions having horizontal and vertical asymptotes. Okay, having done this summary, let's start with the first part. So here, the symbol of infinity, as you can see here, doesn't represent a real number. We should be careful about this. We use this symbol just to describe the behavior of a function when it grows increasingly large, or it grows in really huge in the negative direction. So for example, for this function here and here, when x goes to 0 from right direction, or when x goes to 0 from left direction, okay, this is x goes to 0 from right, you can see that the values of the function grows increasingly large. So we describe such a behavior of function by using this symbol, okay, plus infinity. And now let's think about when x goes to 0 from left. This time you see our function decreases to minus infinity. So it grows too fast, too huge negatively towards minus infinity. This kind of behavior is described by putting here minus infinity, okay? So in both cases, we still say limit does not exist, okay? Let's put this remark here. But here, even if we put equality sign, since infinity is not a real finite number, it is not, we say that limit still does not exist. What is the difference between saying something like this, for example, does not exist? What is the difference between saying limit does not exist and or putting equal to infinity sign? So there is a difference between these two. Here, if you say this limit is infinite, you are giving an extra information that your functions grows too huge towards really big numbers, okay? But still, limit doesn't exist. Also, in this case, it is the same. And let's also look at the behavior of this function around x goes to plus infinite or x goes to minus infinite. As you can see from the graph, please look at this part. This describes the behavior of your function as x goes to plus infinity. As you can see, the values of your function gets closer and closer to 0. That's why we put here 0. And if you investigate the behavior of your function on this part as x goes to minus infinity this time, again, you see that the values are getting so close to 0 again. Okay. So we may have infinite limits as a result of the limit, or you may look at the limit as x goes to plus or minus infinity. Let's move on to the next section. I think you remember that in my previous lecture videos, we go over the limit laws when x goes to some finite number x0. So there were these natural limit laws saying that limit respects to addition, subtractions, scalar multiplication, and so on. And all those limit laws still valid for these kind of limits as x goes to plus or minus infinity, okay? For example, look at here, please. Here we want to compute the limit as x goes to plus infinity. All those natural limit laws are still valid for this case. That's why you can just distribute limit to this summation so that you obtain this. limit of a constant function is itself. And here, what is the limit? We just analyze the limit of this function as x goes to plus infinity, you see. As x goes to plus infinity, this function goes to 0. That's why the limit of this part is 0, so you obtain the result. And you see a quotient here, but you can see this rational function as a product of 3 different functions so that you can distribute the limit to these products as it is the natural thing to do. So after distributing, this is constant, so it is as it is. And we know what is the behavior of 1 over x as x goes to plus or minus infinity. You see, here our function is 1 over x. In all those computations, function is 1 over x as it is indicated here. So as x goes to minus or plus infinity, 1 over x goes to 0. That's why the result here is 0. Maybe right at this point, I can put here a small recall about these certain quotients, like 1 over plus minus infinity is always 0. And if you divide 1 by 0, what happens then? The result is infinite. Another case, or I can write here any finite number divided by plus or minus infinity is 0, and any finite number again divided by 0 is any finite number divided by 0 is what? Okay, it should be a positive finite number. Let's put positive finite number divided by 0 is infinite. Okay, let's put this recall box here. It reminds you this kind of ratios. Let's move on. Okay, what should be our strategy to compute the limits at infinity of rational functions? Okay, here is the strategy. You will look at the highest power of x in the denominator, and you will take this highest power out from the parentheses, and you will start simplifying things. Okay, what I mean here is, let's look at the first example. We want to compute this limit as x goes to infinity. By the way, if you insert infinity for x's here, what you obtain? You obtain infinity over infinity, which is an indeterminate form, okay? I want to put another recall here about this. 0 over 0, infinity over infinity, 0 times infinity, they are all indeterminate forms. Indeterminate forms. Okay, so here we have infinity over infinity, which is an indeterminate form. So we should invent something to obtain the result. Look at the powers of the polynomials here, 5 over 3 and 8 over 5. So 8 over 5 is the biggest power, so that we should take the parentheses according to 8 over 5 here, okay? So what do we obtain? X over 8 over 5. So just do the computation. I mean, to obtain 5 over 3, you should put here what? I think 1 over 15. And then keep doing like that. Minus 19 over 5 should be the second power. And plus 7 times 8 or x to the power 8 over 5, okay? So this also should be a minus. These are the new powers after you took this common factor out. And then at the denominator, what we have, 1 plus 3 times minus 3 over 5, okay? 3 over 5 plus x to the power minus 11 over 10 again. Okay, you can check if we got the correct powers here once you multiply and sum up all those powers to obtain the powers on the left. Okay, after doing this, now you see we obtain a nice simplification. So the next line, after simplifying things, looks like this then. 2 times x to the power 1 over 15 plus x to the power minus 19 over 5. Maybe I can write this minus power by taking this expression to the denominator. You will see why I am doing this in a minute. Okay, I am just taking this minus power, rewriting these minus powers by putting them to the denominator as plus. Okay, like that. And then at the denominator, you can do the same. 3 times 1 over x to the power 3 over 5 plus 1 over x to the power 11 over 10. Now we are ready to compute things. As x goes to infinity, 1 over infinite. What is 1 over infinite? It is 0. So this part goes to 0, 0, 0, 0, because we are sending x to infinity. So what remains then? This is limit x goes to infinity, 2 times x to the power 1 over 15. So what is the result? If you send x to infinity, infinity to the power something is always infinite. Okay, this is how you should proceed once you have a polynomial over polynomial and x goes to 0. Okay, you will take the highest power of x as a common multiple in front and you will start simplifying things. Okay, this will be an exercise for you. Very similar exercise. Next item is horizontal asymptotes. So here is the definition, formal definition of an horizontal asymptote. What does it say? Okay, let me try to explain it by drawing pictures, which are always helpful. Okay, so we have a function and let's say we have such a function. Let's use 1 over x. Maybe I should change the color for the graph. Okay, this is y equals 1 over x. And as we already discussed the behavior of this function as x goes to minus infinity and plus infinity, you see what kind of behavior is this? Here we see that limit of 1 over x as x goes to infinity is 0. And similarly on the other side, here, limit of this function as x goes to minus infinity is 0. So if your function approaches to a finite real number as x goes to plus infinity or minus infinity, then that finite real number, which is 0 in our particular example, is called an horizontal asymptote. In fact, we are not calling this number as a horizontal asymptote, but this equation as the horizontal asymptote, okay? So also from here, you see that y equals 0. This is a line, okay? This is a line. You see, it is this line here. Y equals 0, maybe I can emphasize it. So this is the line y equals 0, which is the x-axis, obviously, and we call it as a horizontal asymptote, And the general definition is if your function converts to a finite real number, then you take this line as your horizontal asymptote, okay? Horizontal asymptotes may look differently. Okay, this was our first particular examples. Let's put other ones. Here, as x goes to minus infinity and plus infinity, the function approaches to the same line, which is y equals 0. But a function may have 2 different horizontal asymptotes. For example, okay, let's put this line here, y equals 1, and let's put this line here, y equals minus 1. And your function may behave like on this side, it behaves like this line. Okay, it is very close to this line. And it goes like this and do this. You see, for this y equals f of x function, y equals 1 is the horizontal asymptote as x goes to infinity. That's why you are calling y equals 1 as a horizontal asymptote. And okay, it is this behavior here. What happens here? On the other part, here, let's look at the limit and investigate the behavior of our function as x goes to minus infinity. You see this time, all the values are approaching to y equals minus 1 line. So the limit is minus 1. And this line is the horizontal asymptote on this side, okay? So this example shows that a function may have two different horizontal asymptotes, or they may be the same as in this case. Okay, next, here is another example, e to the power x. This is the exponential function. Let me draw the graph of it. So e to the power x function is this one, exponential function. And here, at this part, if you analyze the behavior of it, as x goes to infinity, but our function goes to 0. Okay, so let me rewrite it again. Limit of this f of x as x goes to infinity, limit of e to the power x as x goes to infinity. As x goes to minus infinity, obviously not infinite, but negative part, minus infinity. So what is this? This is e to the power minus infinite, 1 over e to the power infinite. So it is kind of 1 over infinite, which is 0. That's why now we will call this y equals 0 line, which is the x-axis. It is in fact y equals 0 line as the horizontal asymptote of this function. Okay, so let me move on. Here is another example. You can study this example by yourself. I leave it as an exercise and I will solve for you this one. Here, by computing the limit as x goes to plus or minus infinite, it was easy. In the previous examples, we just compute things or we just look at the graphs to see the limit. Sometimes the computation may not be that easy and we can use sandwich theorem. Sandwich theorem holds also for this case as x goes to plus or minus infinity. Okay, let me see. Let me show you a next application of it. Okay, what we want to show. Find the horizontal asymptote of this function here. All you need to do to find the horizontal asymptote of it, to find the limit of this function as x goes to plus or minus infinity. Okay, let me write this part. Okay, we are searching for the horizontal asymptote. To find it for this function, what is the function here? This is our function, 2 plus sine x over x. So we will look at the limit of this function, sine x over x as x goes to, let's start with plus infinity, okay? Okay, what is this limit? You see sine infinity over infinity. This is not an easy limit to compute. So we will get help from sandwich theorem in this case. So to be able to apply the sandwich theorem, you should start by some inequalities related to your function. What we know is that sine function takes the values between minus 1 and 1. And now by playing with this function, I will try to obtain this one. I can now divide as x goes to plus infinite. It is obviously a positive number. Now I can do what? I can multiply each side by 1 over x, which is a positive quantity, okay? So let's do this. After multiplying every side by 1 over x, my function will become like that. Okay, maybe sine x over x, and the right side will be like this. You see, I obtained this part now. All I need to do is to add +2 both sides. Okay, now what I am doing, I am adding +2 to each side. 2 plus sine x over x less than or equal to 2 plus 1 over x. Okay, now I obtain a very nice inequalities bounding my function from above and from below. Now what I should do, I am ready to send x to infinity to see the limit of the upper bound and lower bound function. If x goes to 0, what happens to this function? This part goes to, sorry, if x goes to infinity, this part goes to 0. That's why this expression goes to 2. And similarly for the upper bound, it goes to 2. What does this say by sandwich theorem to you? Then by sandwich theorem, the middle function has to have the same limit. So x2 plus sine x over x goes to infinity is 2, because the lower and upper bounding functions has the same limit as 2. So you see, as x goes to infinity, we obtain a finite limit, finite number. So this line should be the horizontal asymptote of the given function, okay? You see y equals 2 line here, it is the pink one. And this is the graph of the given function, and it approaches to y equals 2 as x goes to infinity. We analyzed this part of behavior. And similarly, you can do the computation for as x goes to minus infinity. So limit x goes to minus infinity of this function sine x over x. I will leave this part as an exercise. It is similarly to above. You will obtain again 2, and its behavior as x goes to minus infinity is again, your function gets closer and closer to this y equals 2 line, which is horizontal asymptote. And in this example, what you see that your function may intersect, obviously your function may intersect its horizontal asymptote, okay? There is no rule that function never intersects their horizontal asymptotes. No, this is not correct. In fact, your function may intersect its horizontal asymptote as it happens here. Okay, let's write this down. Function may intersect its horizontal asymptote, and in this case, they intersect infinitely many times. Okay, this is a remark or a warning for this function, for this example. Okay, so this is a nice example showing that a function may intersect its horizontal asymptote. Okay, next kind of asymptote is the oblique one, oblique asymptote. Okay, this is the second case. We covered horizontal asymptote, now we are looking at oblique one. Okay, in fact, oblique asymptote is kind of a generalization of the horizontal asymptote. Why? I will explain. Let me start drawing things just to explain clearly for you. Okay, so if your function, okay, look at this graph, please. And let's, instead of drawing a horizontal line, now I will draw a slanted line like this. Let's say this line has this equation ax plus b. And let me draw now a function like this, okay? Maybe I can just draw it again, like this one. This is y equals f of x. Now, what we are going to do, we will investigate the behavior of our function again, which is the blue one, as x goes to minus infinity. Okay, what you see here, as x goes to minus infinity, our function behaves like this line, right? Our function behaves like this line, which means if I take the difference of my function with the given red line, which has this equation ax plus b, what is your guess? What should be this limit? As x goes to minus infinity, your function behaves exactly like this line. So there will be no difference between them. That's why we expect this limit to be 0. And similarly, this kind of situations may happen at the plus infinity case. So let's put our line again here. It is ax plus b, and consider a function like this. Okay. You see, as x goes to plus infinity this time, look at the behavior of your function here. What happens there? Here, we see that as x goes to plus infinity, okay, our function behaves this is y equals f of x function, our function behaves exactly like this line, so that there is no difference between them as x goes to infinity. That's why if I try to take the difference of them around infinity, I will obtain what? We expect to obtain nothing because they just behave like the same. So this limit should be 0. That's why we define oblique asymptote like this. This is not a horizontal line anymore. It is more general. More generally, it is a slanted line like this. So this kind of lines is called oblique asymptote. Oblique asymptote, okay? If this kind of behavior happens, of course. So this is the oblique asymptote of the given function again. So I think we understand why the oblique asymptote is defined like this, because there is no difference around minus infinity or plus infinity between your function and this slanted line, okay? Y equals ax plus b line. Okay, so geometrically, the explanation is like this. But is there an algebraic way to detect oblique asymptotes? The answer is yes, because we don't always have the graph of the function. We don't know the graphs of function every time. Sometimes we may have so complicated functions of which we don't know the graph. And that in that case, you can still detect the oblique asymptote algebraically. There is an algebraic way. In fact, it is written here. If the degree of the numerator of a rational function is one more than the degree of the denominator function, then that function has oblique or slant asymptote. How do we find the equation of the oblique asymptote, which is in the form of ax plus b? You will just perform the polynomial division, okay? By dividing the numerator to the denominator, and you will see the result. That result will give you the equation of the oblique asymptote. Okay, let me summarize that part also here. So let me say remark. This is the algebraic way of detecting oblique asymptotes. Let's say you have a rational function like this, px over qx. If you look at the degrees, okay? If the degree of px numerator function is one greater than the degree of qx like that. So if the degree of p is one more than the degree of the q polynomial, then this means that there is an oblique asymptote. If this happens, then you say that then f of x has an oblique asymptote. And how to find it? Find it by performing polynomial division. You will do this polynomial division, you know from the high school how you do such divisions between polynomials. So you will do complete this division algorithm. You will find a remainder here, and this part will give you your oblique asymptote equation, okay? Whatever you see here is the oblique asymptote for your function. Okay, so after doing this polynomial division, how do you re-express your function? Let me remind. So px over qx can be rewritten in terms of rq and this like that. You write it like ax plus b plus remainder over qx. Okay, this part is your oblique asymptote. Okay, let's try to apply this kind of stuff in an example. Okay, our first example, find the oblique asymptote of this graph. You look at the degrees, please. Okay, degree of the numerator is 2, while the degree of the denominator is 1. Degree is 2, degree is 1. So, you know, if you add +1 to this one, you obtain this. That's why, you know, this equation holds, degree of the numerator is 1 more than the degree of the denominator, so there is an oblique asymptote. Oblique asymptote, how you find that? Let's perform polynomial division to find that. This should be divided to 2x minus 4. So we have x squared here, you need to multiply with x, but you also need to get rid of this coefficient here. That's why I need to multiply with 1 over 2 times x. So it is exactly x squared, then minus 4 times this is minus 2x. Then you take the difference, it becomes 2x minus 3 plus 2, you need to multiply 2x minus 8, take the difference, and what you obtain? You will obtain 5, I guess, right? Okay, and sorry, did I? Yes, I think this should be 1 for this mistake. Okay, let's fix it. If you multiply with 1, it is 2x minus 4, take the difference 1. Now you see this part gives you your oblique asymptote. Y equals 1 over 2x plus 1 is the equation of a line, which is a slanted line and which serves as the oblique asymptote for your function. Oblique asymptote. Okay, so from this division, you can rewrite your function as f of x, which is given as this quotient, 2x minus 4, can be rewritten as 1 over 2x plus 1 plus remainder over 2x minus 4. Okay, you see your oblique asymptote here. And this is the algebraic way of detecting oblique asymptote. How do we see it from the graph? You see, this is our function, y equals x squared minus 3 to x minus 4. And after applying polynomial division, we find that this part is the oblique asymptote. And you will see that slanted line here, the pink one, this one, okay. It is this line here. And as x goes to plus or minus infinity, your function gets closer and closer to this red line, which means, which shows it is the oblique asymptote for our function. Okay, so let's move on. Now, we will look at the case where the limit is infinite. Now, this time, we won't look at limit as x goes to plus or minus infinity. Instead, we will have the situations like the result is infinite. Okay, please, before going over this part, I want you to look at this graph and consider how 1 over x function behaves around the origin, okay? If you look at this function as x goes to plus infinity, as x goes to 0 from right, what happens? Let's try to investigate this thing again. Limit of 1 over x as x goes to 0 from right, then you see your function grows increasingly large. So the values kind of diverge to 2 big numbers, and this kind of behavior is denoted by putting plus infinity. Okay, this is not a real number. Be careful, it is not a real number, and it is just a notation to describe the behavior of a function who grows increasingly large, okay? So by putting infinity here, we don't say, this doesn't mean that we don't say limit exists. In fact, limit does not exist. Limit still does not exist. What we say is we are giving an extra information describing the behavior of the function, which is growing too much. Okay, so it is also highlighted here. Putting infinity here doesn't mean that limit exists, nor we are saying that there is a real number as infinity. This is just a description of the behavior of our function where the function grows too big. And similarly for the other direction, you see, in this direction, what happens? In that direction, as x goes to 0 from left, you will look at here. Your function decreases too big. So to describe this kind of behavior, you put minus infinity. Limit still does not exist, but we just have these symbols to describe the behavior of the function. Okay, so, and these kind of behaviors also happen for this function, which is 1 over x squared. Remember, this is y equals 1 over x. If you put an extra square here, then all the negative y values gets like taking the symmetric version of it, and the graph of 1 over x squared looks like this. And you can look at the limit of this function as x goes to 0 from right and x goes to 0 from left. Okay, let's analyze. From right grows too big. There is a certain symbol that we use to describe this kind of behavior, and similarly from left, it grows too big again, so both limits are infinite. Okay. So let's move on. Here is a nice example showing us rational functions can behave in different ways near zeros of the denominator. Okay, let's compute the first limit quickly. Limit as x goes to 2. So what we have here, x minus 2, 1 more x minus 2, and the denominator can be decomposed like this, x plus 2, x minus 2. And then these are canceling. That's why we have x minus 2, x plus 2 as x goes to 2. Just insert 2 for x, so 0 over 4, which is 0. And what changes if you cancel this square here? Let's try to see. Limit as x goes to 2, x minus 2, x minus 2, x plus 2. To simplify things, and you will obtain limit as x goes to 2, 1 over x plus 2. So what is this limit? It is obviously 1 over 4, a finite number. And let's look at here. What is the common property of all those examples? All of them have denominator 0 as x goes to 2. So we are trying to understand here the functions having zeros at the denominators may behave differently. Okay, for example, this function behaves like 0. This function has limit 1 over 4 around the 0 of its denominator, and one more, x squared minus 4 as x goes to 2. So what 2 from right? Okay, so this is a one-sided limit. We are approaching 2 from right, so we are putting kind of this kind of 2.00001 number. So denominator will obviously get 0. Nominator, if you insert 2 here, is minus 1, and denominator approaches to 0 from the positive direction, right? So I will write here goes to 0 from positive direction. That's why minus 1 divided kind of 0, which is a positive number, I mean, a really small number around 0, which is positive. So this is minus infinite because of this minus here. And look at this limit, x minus 3, x squared minus 4. This time we are looking on the other direction. 2 is here, and we are approaching from left, so that you insert for x like 1.999 number. Then this is again minus 1, and denominator goes to 0 from negative direction, right? From negative. That's why minus 1 divided by a minus number, which is really small. That's why this time it is plus infinite. Okay, let's look at this limit as x goes to 2. So we look at right-hand side and left-hand side limits. One of them is minus infinite, one of them is plus infinite. That's why you can directly conclude here it is the same function. So limit does not exist by these two. Okay, the last one. What do we have here? You can rewrite this expression as minus x minus 2 and simplify. Then you will obtain 1 over x minus 2 squared. So this is kind of dividing 1 by 0, so it is plus infinite. Okay, so these examples shows us different kind of behaviors around the zeros of the denominator. This is related to vertical asymptotes, which is our next topic, okay? So what's the vertical asymptote? If your function behaves as plus or minus infinite around some finite real number a, then this line x equals a is called a vertical asymptote. Okay, let's highlight also from the formal definition. X equals a is a vertical asymptote if around a from right or from left direction, your function gets really big or really small numbers like plus or minus infinity. So for example, let's choose a as 3. And here you see that if you look at limit of this green function as x goes to 3 from, okay, this is our y equals f of x function. If you look at the limit of it as x goes to 3 from left, what happens? Look at the behavior here. The limit is plus infinite, right? It is plus infinite. And if you look at the limit from the other direction, as x goes to 3 from right, okay, this time you're approaching from right, and in this case, it is still plus infinite. So you see this is satisfied. That's why we call now x equals 3 as a vertical asymptote of the given function. So there are three different situations here which shows you around the vertical asymptote, your function may behave differently. So on both sides, your function may go to plus infinity, or on one side, your function may go to minus infinity, or on the other side, it may go to plus infinity, okay? On this side, it may approach plus infinity, or on one side, the limit doesn't need to be infinite, but on just one other side, like this one here, limit of the function as x goes to, okay, let's put this as 3 from right. What is the behavior here? Your function goes to minus infinity. Okay, these are different situations around the value of vertical asymptote. On both sides, your function gets plus infinite, may get plus infinite. So on one side, it may go to minus infinity, while on the other side, it may go to plus infinity, or the infinite plus minus infinite value may appear at just one side, as in this case, okay? In all the cases, x equals 3 is a vertical asymptote, okay? X equals 3 is a vertical asymptote. So all you need to do is to look at the limit around the 0 of the denominator. If this limit becomes plus or minus infinity on one direction of that number, then this is enough to conclude that x equals a is a vertical asymptote, okay? So do you remember what is a horizontal asymptote? We have just covered 10 minutes ago. So maybe I should recall it so that you saw the difference and you remember things correctly. Okay, this is vertical asymptote, which is a vertical line. What was the horizontal asymptote? Horizontal asymptote is a horizontal line to which your function approaches. For example, like that. So this is y equals f of x. If you look at the limit of f of x as x goes to infinity, let's say this number is 1 here, is 1. Okay, and limit x goes to minus infinity. This may be a different line, but in my picture, it is still the same horizontal line, you see? So here and here, we see that y equals 1 is a horizontal asymptote. The name tells you everything. Vertical asymptote is a vertical line, and around this vertical line, your function gets too big or too small values like plus minus infinity. But in the horizontal asymptote, you are looking at the limit as x goes to plus or minus infinity. The result of the limit should be a finite number, and you call y equals that finite number as a horizontal asymptote. Okay. So what else? We can work on this example. Find the horizontal and vertical asymptotes of this function. Okay, let's go over it. Okay, first of all, horizontal asymptote. How do we detect horizontal asymptotes algebraically? We look at the limit of the function as x goes to plus or minus infinity, right? Let's consider these cases separately. Plus infinity. So what is the limit here? Normally you see infinity over infinity, but if you compute things by looking at the highest power of the polynomials, we did this in this video. So x parenthesis 1 plus 3 over x, x 1 plus 2 over x. So now you are ready to send x to infinity, so that this part goes to 0, 1, 3 over infinite, 0, 2 over infinite, 0. That's why after simplifying these two things, the limit is 1. So y equals 1 is a horizontal asymptote for this function. And the limit will exactly be the same if you look at as x goes to minus infinity, okay? Plus minus infinity is computed as the same. So there is only one horizontal asymptote of this function, which is here. Y equals 1 is a horizontal asymptote, and your function approaches to y equals 1 line as x goes to plus or minus infinity, as it's seen from the graph. What is the vertical asymptote here? To detect vertical asymptotes, you search for the zeros of the denominator, okay? Let me write that down here. Search for the zeros of the denominator function. What does this mean? You look at the denominator, x plus 3, x plus 2. So you see that at x equals minus 2, denominator becomes 0. So this is a candidate for a vertical asymptote. It is, we don't know yet whether it's a vertical asymptote or not. It is just a candidate. How do we prove that it's a vertical asymptote? Of course, by checking out these limits. If one of these limits turns out to be plus or minus infinity, then I will conclude that x equals minus 2, this is a vertical line, is a vertical asymptote. So x plus 3, x plus 3 over x plus 2, let me rewrite it, plus 3 over plus 2 as x goes to minus 2 from right. We will look at this limit, and we will also look at the other limit, other one side limit. X goes to minus 2 from left. Okay, so what is this? It is, in fact, 1 over, so you are approaching minus 2 from which direction? In the first case, we are approaching from the right direction. So here, minus 2 is here, and we are approaching, sorry, in this case, we are approaching from right. So you are kind of putting minus 1.999 or something. That's why you will obtain here a really close number, which is positive. So very little positive number, so small, which means that you are kind of dividing 1 by 0, kind of 0 number, which is positive. So it is plus infinity. And you can think similarly here. Okay, let's look at the case. This time you are approaching from left. So you are inserting minus 2 to 0.0001 kind of number. That's why this denominator will be negative. Very small number. it is kind of 0, but the important indication here is that it will be negative, okay? That's why the result is minus infinity. You see, as x approaches to this number on both sides, we get plus or minus infinite. That's why this proves that x equals -2 is a vertical asymptote. Let's investigate also from the graph. As x goes to -2 from right, we find plus infinity. So it describes this behavior here. On the right side of -2, your function gets too big. And as x goes to -2 from left, okay, from left, then if you approach from left, we find minus infinity. You see, it describes this behavior here. That's why we call x equals -2 as a vertical asymptote, okay? So we can also look at this case. Y equals ln x is this function. And if you look at the limit of this function around 0, limit of ln x as x goes to 0 from right. So we are looking from this direction and you see the behavior, your function gets so small. I mean, it grows too big negatively. That's why this limit is minus infinity. And that's why you can conclude that x equals 0 is a vertical asymptote for f of x is ln x, okay? And also for this one, this time there is no, for e to the power x, we already covered this function above. As you remember, this function has a horizontal asymptote, which is x-axis, y equals 0 line is a horizontal asymptote for e to the power x, because if you look at the limit e to the power x as x goes to minus infinity, it is 1 over e to the power infinite. So 1 over infinite is 0. So y equals 0 is a horizontal asymptote for this function, which is exponential function, okay? And here there are more examples. You can check this example by yourself. Let's put exercise for this one. And finally, I put here a very nice summary for you by removing technical details, but by just putting the graphs. So what is a horizontal asymptote? It is a horizontal line like that. It is this line here. For example, y equals 1 line. This is a horizontal asymptote, as you can see, because the limit of your function as x goes to infinity approaches to this real number 1. That's why y equals 1 is a horizontal asymptote, okay? So, for example, this function has a horizontal asymptote here. Let's say this point is 1. Y equals 1 is a horizontal asymptote. And here, on the other side, it approaches y equals -1. As x goes to minus infinity, the behavior is this kind of behavior, as you can see. That's why this line y equals -1 is also an horizontal asymptote. So a function may have only one horizontal asymptote or two different horizontal asymptotes, and your function, okay, let's say this is the point 1, y equals 1, still is a horizontal asymptote here, even if your graph intersects it infinitely many times. Okay, what's a vertical asymptote? Around a vertical asymptote like this, for example, x equals 1, your function should get plus infinity or minus infinity. So in this case, on both sides, your function gets plus infinity. So x equals 1 is a vertical asymptote. But this may also happen. On one side, it may get plus infinite. On the other side, it may get minus infinite. Still, you call this x equals 1 line as a vertical asymptote. And there is also this case. On one side, there won't be any infinite plus or minus infinite values, but on just one side, only on one side, if you have, let's say this point is 1, x goes to 1 from right, this limit is what? Minus infinity according to this picture. Only on one side, if you have plus or minus infinite, you still conclude that x equals 1 is a vertical asymptote. You don't need to have plus or minus infinities on the other side too. No, on one side, minus infinite, this is enough to say that that vertical line is a vertical asymptote, and slant asymptote is in fact the generalization of horizontal asymptote. The only difference is that your line is not horizontal anymore, but it is a slanted line. This kind of lines has a x plus b form, and you see here, if, as x goes to plus infinity, your function, which is the red one, behaves exactly like this slanted line. So your function approaches to this line as x goes to infinity. Okay, that's why you call this line as an oblique asymptote. So this is the summary of 3 kinds of asymptotes, and I put here 3 more pictures at the end of your lectures so that you can analyze them. For example, just let's look quickly at them. This line, which is the x equals 0 line, is a vertical asymptote because on the right side and on the left side of x equals 0, your function gets plus. On the left, it gets plus infinity. Sorry, on the right, it is plus infinite. On the left, it is minus infinite. That's why this is a vertical asymptote. And y equals 0 is a horizontal asymptote because as x goes to infinity, limit of your function is what? Is 0. And you see from here that limit of your function as x goes to minus infinity is 0 again. So y equals 0 is a horizontal asymptote. You will see a slanted asymptote here. Okay, this is an oblique or slanted asymptote, and we see a vertical asymptote too here in this case, because on left and right side of 1, your function gets plus infinity or minus infinity. That's why x equals 1 is a vertical asymptote. And in the last case, we have this horizontal line towards which your function approaches as x goes to plus infinity or as x goes to minus infinity. This is which line? This is y equals 3 line. This is a horizontal asymptote. And there are 2 vertical asymptotes. One of them is x equals minus 5, vertical asymptote. The other vertical asymptote is x equals 1 because of this getting minus infinity, and plus infinity values are around those numbers. Okay, so I stop here. Thank you for listening.